Well, also in granites and schists. Now I add here schists, metamorphic rocks. The reason why I keep on emphasising that this is both in granites and schists, we find biotite grains, which is a black flaky mineral. It's called mica, and the black variety is called biotite. The white variety is called muscovite. The reason I'm mentioning schist as well as granite is because some of our critics try to tell us that what I'm going to talk about, radiohalos, form in granites by a different process. But wait a minute, that same critic does not recognise that these same radiohalos form in schists, in metamorphic rocks, which is a totally different rock. And so he's blind. He's focused on granite, and nobody else agrees with him, by the way, on his argument for the formation of granites. Mainstream scientists do not accept his idea for the formation of those granites. And these radiohalos are also found in schists. So I mentioned that right up front. So embedded in the biotite grains, okay, not only are zircon grains found in the granite overall, but sometimes tiny zircon crystals are embedded within these black biotite grains. They got trapped between the layers called the sheets, the mica sheets, the crystal sheets of biotite. You actually peel a biotite flake apart like the pages of a book. The zircon crystals have been trapped between the pages of the book. And so the zircon grains within the biotites contain radioactive uranium atoms. They decay and they eject alpha particles. Okay, we're familiar with that process. And each uranium atom goes through 8 decay steps. So there's 8 different alpha particles. At each step, it's a different daughter atom that spits out the alpha particles. Because it takes 8 steps to get down to a stable lead atom, but in the process there are different daughter atoms that become the parent for the next step of the alpha decay chain. Okay? And we know what those elements are. So when the zircon crystals are large, for example, 60 microns long, that is about 6 times the thickness of your hair, the alpha particles stay within the zircon crystals and they become helium atoms within the zircon crystals. However, when the zircon crystals are only tiny, only 1 micron in length, the alpha particles escape from the zircon crystal and they're ejected out into the surrounding biotite flakes. Okay? So here on the diagram on the right, you can see the little grey dot. That's the zircon crystal. Each of those arrows in 3 dimensions is spitting out in a spherical halo these alpha particles, okay? And these alpha particles are like little bullets. They damage the crystal structure of the biotite around them, discolorating it. And those discolorated areas are in a sphere or a halo. And because it's produced by radioactivity, it's called a radioactive halo, or radiohalo for short. Okay? And you'll see on the right, there's a darker area and there's a lighter area. And you can see the little zircon crystal at the center of the flake. And I want you to notice something else. The biotite flake that hosts us is both brown and green. That's because the biotite flake has been altered to green as a result of hot water. That's an indication. The biotite flake, when it's pristine, is usually brown. When it's altered by hydrothermal fluids, hot waters, it turns green. Okay. So at each step of the alpha particle decay chain, okay, uranium decays with 1 alpha particle step, it goes to uranium-234, decays to 238, to 230 thorium, decays to 226 radium, decays to 222 radon, decays to 218 polonium, 214 polonium down to 2110. At each of these steps, the parent atom shoots out an alpha particle of a different energy, okay? And different energies mean the different bullets travel different distances, okay? It's like having a handgun and a rifle. A handgun won't shoot the bullet as far as a rifle. The rifle will shoot it at a greater distance. And it's like that. Think about firing a gun into a drywall. It'll damage the drywall. So it's like that. The alpha particle bullet will damage the crystal around it. Okay? It's been determined that a fully formed dark uranium radiohalo, which has 8 rings, you can see it there, fully formed, it requires between 500 million and a billion alpha particles. Okay, it takes that many to leave enough damage to make the darken the biotite sufficiently so that we can see it. And that amount of alpha particles is equivalent to at least 100 million years worth of radioactive decay at today's measured decay rate. Okay, so every radio halo that you can see under the microscope, because these are examined under the microscope in the biotite flakes, every radio halo takes at least 100 million years worth of radioactive decay to produce it. Now, granites and schists around the world, and I've looked at samples, and others have too, from around the world. Some of this is in the open scientific literature. It's been known for over a decade about these radiohalos, and from schists as well as granites. And that means all these granites and schists contain observable physical evidence of abundant nuclear decay of at least 100 million years worth of decay at today's measured rate. But in many granites and schists, okay, we've now looked at radiohalos in general. Uranium radiohalos, a fully formed uranium radiohalo. Now let's look at what are known as polonium radiohalos, because in many granites and schists, not just granites but also schists, the biotite flakes in them have radiohalos consisting of only one small ring, and we find them alongside the uranium radiohalos, as in this example here. And the diameter of that one small ring matches the energy of polonium-210, the last step. So that means this one ring small radiohalo was parented only by polonium-210. In some granites, we have biotites and with flakes, granites and schists, with radiohalos consisting of only 2 rings. And they're alongside dark uranium radiohalos that are fully formed. Now, this dark uranium radiohalo, by the way, has had so much decay that the inner rings are lost. It's very, very dark. So that's well over 100 million years worth. And the arrowed radiohalo there has only 2 rings. And those 2 rings fit with the energies of the polonium-214 and the polonium-210 parent atoms. And so that means this 2-ring radiohalos was parented the outer ring by 214 decay, polonium-214 decay, the inner ring by polonium-210 decay. So because it was parented by initially by 214, we call these polonium-214 radiohalos. And then occasionally in these same granites and schists, there are biotites that with radiohalos that consist of 3 rings. And those 3 rings match polonium-218, polonium-214, polonium-210. And because the first ring was parented by 218, we call these 3-ring radiohalos polonium-218 radiohalos. And notice they are independent of the uranium radiohalos, which means the polonium that parented these radiohalos was independent of the uranium. And that's significant. Okay? These radiohalos were produced by the last 3 steps in the uranium decay chain. And as I said, they're found with uranium radiohalos in many granites and schists around the world. I've just recently published a paper on the metamorphic rocks in the Grand Canyon that contain these radiohalos, as well as granites in the Grand Canyon that contain these radiohalos. Now, these polonium radiohalos, by the way, there was a famous 1989 court case in Arkansas, and in that Arkansas trial, US court case, these radiohalos on the witness stand were called a very tiny mystery. Why are they regarded as a tiny mystery? It's because these polonium radiohalos are so unstable, they only have fleeting existences. Polonium-218 has a half-life, a decay rate of 3.1 minutes. Polonium-214, 164 microseconds. If you blink, it's gone. Polonium-210, 210, 138 days. So that means with such extremely rapid half-lives, these polonium radiohalos had to form extremely rapidly. But here's the problem. How did you get the polonium concentrated? Robert Gentry, who pioneered some of this work in the 1960s, claimed there was no natural processes that could form these polonium radiohalos. He claimed there had to be a concentration of 50% polonium radiohalo in the radio center. That is in a central nucleated part. We call it a radio center, a nucleated center that would then spit out the alpha particles. The zircon grain in the uranium is called the zircon radio center. Well, there had to be a polonium-bearing radio center. And you need at least 50% concentration of polonium, he said, to produce these radiohalos. And so for a polonium-214 radiohalo, you had to have 50% of the necessary 214 polonium concentration transported to form that radio center within a millisecond or two, within a blink of the eye. And that's why he regarded these as indicating the rocks were created. He thought, well, it took the blink of an eye, creation took the blink of an eye, and the radiohalos polonium formed in the blink of an eye. But would God create polonium radiohalos and then allow uranium halos to subsequently form alongside them over millions of years in the same biotite flakes? These coexistent polonium uranium radiohalos are often found in granites and schists. However, that could have formed during the flood. So, for example, others before me and myself looked at granites that had intruded into and crystallized within fossil-bearing sedimentary rock layers. And from a biblical perspective, those fossil-bearing sedimentary layers formed during the flood. And that means the granites formed during the flood, the radiohalos formed during the flood, including the polonium radiohalos. So the granites weren't created. There had to be some other process that could form these polonium radiohalos. It required a new model. Now, think about it. Since this polonium element is a rare element, polonium is a very rare element, how could it form these radiohalos? How could it be concentrated separate from uranium in a separate place from uranium? But here, the radiohalos are in the same biotite flakes. And the only nearby source of uranium in the biotite flakes to where you find the nearby the polonium radiohalos is actually the zircon grains. The zircon grains have uranium that are generating radiohalos, uranium radiohalos in the same biotite flakes. So that means the uranium had to come, the polonium had to come from the uranium that was generating uranium radiohalos at the same time as the polonium was being separated and nucleating to form alongside polonium radiohalos at the same time in the same biotite flakes. So there had to be a way of taking the polonium from the zircon crystals as the uranium decayed polonium to separate locations within the same biotite flakes and adjacent biotite flakes, I might add, to form the polonium radiohalos. And this had to be done. The uranium decay had to deliver enough polonium rapidly to generate 500 to a billion alpha particles for each dark polonium radiohalo to form before all the polonium had decayed. So in other words, the uranium had to be speeded up, its decay had to be speeded up, accelerated to produce enough polonium very quickly for it to be transported elsewhere to form polonium radiohalo before it could decay away. So this was immediately evidence for accelerated nuclear decay of uranium. The polonium radiohalos wouldn't exist unless you had accelerated decay of uranium. Now, by the way, we also found in this research that the slower the decay rate, the faster the acceleration decay rate. So, for example, potassium had a faster decay rate than uranium. Potassium-argon ages were younger than uranium-lead ages. Therefore, uranium had been accelerated more than potassium. And so when polonium has a very fleeting decay rate, means that with accelerated nuclear decay, the polonium decay rate would not have been speeded up all. The same as with radiocarbon, has a very rapid decay rate, so it would not have been affected by accelerated nuclear decay. That's an important point to make before we go on here. So that means at least 100 million years worth of uranium decay has to occur within days to form the polonium radiohalos. So how do we get this concurrent uranium and polonium radiohalos? We need to remember that it's been observed and experimentally determined that radiohalos can only form below 150 degrees C, which geologically is cool. Molten granite forms at 650 degrees C. A basalt erupts at over 1,000 degrees C. Okay, so 150 degrees is cool. But above the 150 degrees, the alpha particles are annealed, they are destroyed. It was found that as they went down that drill hole at Los Alamos, the same drill hole from which the zircons were sampled for their helium diffusion, the radiohalos in the biotites in that granite were also looked at. We knew the temperature going down the drill hole. At 150 degrees, the radiohalos disappeared because they were wiped out. So that means radiohalos can only form below 150 degrees. The uranium radiohalo forms around the tiny zircon crystal. Uranium decays in the zircon to supply the radium and polonium, and we have infiltrating hydrothermal fluids that are under pressure. As the granite cools, the granite releases water, hot water. We know this. As magmas cool, they release waters. We see that at Yellowstone. That's why we've got the geysers. And that water is under pressure, which helps to force it into the rocks, helps to force the hydrothermal fluids between the sheets of the biotite flakes. You know, critics say, but how could the hydrothermal fluids go through the crystal in the crystal lattice? It's because of the pressure at those temperatures. So the hydrothermal fluids travel between the biotite sheets, along the cleavage, which is the break between the pages of the book. The hydrothermal fluids pick up radon and polonium from the uranium that's decaying in the zircon crystal, carry it across to adjacent site. Now, because it doesn't decay in transport, it doesn't usually leave any sign, but in some cases we see staining along fractures. So we know that there's been radiation stains. We know the fluids have transported along the fractures, and radon and polonium have decayed as the fluid has been transported along the fractures. But the polonium concentrates in radius centers, such as where there's a sulfur atom or a chlorine atom, because we know that polonium is like lead. It loves chlorine, it loves sulfur. And as the polonium decays after uniting with a sulfur atom or a chlorine atom, it decays, then the chlorine atom or the sulfur atom is ready to receive another polonium atom from the fluids. And so what happens, progressively the fluids transport the polonium. The radio center sucks up the polonium, decays, sucks up more polonium, decays as more hydrothermal fluids bring more polonium atoms. And so as they're transported, they decay, then more polonium forms on the radio center and eventually builds up progressively as the hydrothermals transport so you don't have to have 50% concentration all at once. All you need is accelerated nuclear decay of uranium at the source and rapid transport hydrothermal fluids under pressure, going along fractures between the cleavage planes, progressively transporting the polonium where it's nucleated in geochemically conducive radio centers where it decays, more polonium is added from more hydrothermal fluid, and it builds up and progressively decays, produce these polonium radiohalos. So what evidence do we have that rapid hydrothermal fluid transport of polonium has produced these adjacent polonium radiohalos? Well, first of all, the short half-lives of polonium-218 and 214. 3.1 minutes and 164 microseconds. Unless it's rapid, you don't form those polonium radiohalos. The distances of transport are short. They're less than a millimetre within the same biotite flakes usually. Furthermore, we now have empty bubbles at the centres of nearly all the polonium radiohalos. That means they were fluid bubbles, fluids that contain the polonium radiohalos that is no longer there. And the last evidence is my research has shown the greater numbers of polonium radiohalos are found where there were greater volumes of hydrothermal fluids involved. And you can go on the webs, you can go to the literature and you can see my papers on radiohalos where I tested this, and I found that where there were greater quantities of hydrothermal fluids, you always found greater numbers of polonium radiohalos. So there are these supporting evidences that this was the case. So what conclusions do we reach? Dark uranium radiohalos in many granites and schist metamorphic rocks around the world are observable physical evidence that abundant nuclear decay has occurred at least 100 million years worth at today's measured rates. And coexisting polonium radiohalos in many granites and schists around the world had to form at the same time, and so observable physical evidence that this abundant nuclear decay had to occur at an accelerated rate. Such an accelerated decay rate would be expected to generate enormous volumes of heat, as some argue, and that would have potentially caused a major heat problem. And you'll get critics that will say, oh, but it would have melted the rocks. But wait a minute. We know from observed and experimentally evidence determined that radiohalos can only form below 150 degrees C. Otherwise, the tracks disappear. So there cannot have been a heat problem. Otherwise, there would have been no radiohalos to have survived. So the very existence of the radiohalos indicates that there was no heat problem when these radiohalos formed as a consequence of this accelerated nuclear decay. It means that there must have been some other process that dissipated all that heat, supposed heat.
What's the secular explanation for the radiohalos?
Well, G. Brent Dalrymple on the witness stand at the Arkansas trial in 1909 said it was a very tiny mystery.
Mystery.
And the only person who has really critiqued the radiohalos is, again, Lawrence Collins. And he tries to tell you that it's because I got it wrong about the way granites form. They form by a different process called metasomatism. But he fails to mention that the features he refers to, myrmekites, aren't recognised in all the granites that are, and they're not in many of the granites that I looked at. And the secular community ignores or doesn't appreciate or doesn't recognise his methodology for explaining granites. It produces hot water anyway, and you know he's not explaining why you got polonium radiohalos in schists in metamorphic rocks. Myrmekites don't form in metamorphic rocks. He's just ignoring. He's just selective in some of the data he used. He claims that it's radon, but wait a minute. If they were radon halos, radon is an inert gas. Radon will not be geochemically concentrated in any one location because it's geochemically inert. Polonium is chemically active. It has the same valence as lead. And so it's geochemical. And I looked this up. There's a volume published in 1957 on the geochemistry of the rare elements. And you can look up polonium and it's got all the geochemical details. And it was a eureka moment when I found that in the University of California, San Diego Library on a Sunday afternoon at over there in San Diego area. And suddenly I saw the connection. Polonium connects with sulfur, connects with chlorine, and that's can sit between the biotite crystal flakes in the cleavage planes where the hydrothermal fluids are being transported. Radon won't do that. It's geochemically inert. So you can't have radon radiohalos. They don't exist. Nobody's ever recognized them. And Lawrence Collins will say, oh, but you misidentified the halos. They're really radon halos. No, I didn't misidentify them. Robert Gentry identified them based on 1, 2, and 3 rings that equates to the energy levels produced by bombardment by alpha particles of energy parented by 218, 214, and 210 polonium. End of argument.
So a lot of good points there. You remain unpersuaded, or would you say that the best arguments, and I'm not even saying they're good arguments, that critics like Lorence G. Collins are offering, they're not very persuasive in actually addressing the data of radiohalos, Dr. Snelling?
All the data. You can select things, and but you haven't taken into account the total picture, the geochemistry of the rocks, the fluids, what rocks, where, schists, metamorphic rocks, as well as granites, where you've got more hydrothermal fluids, you're getting more radiohalos. All those things, all those factors he's not taking into account.
So in light of all that, then, those are some very important points. Going back to this issue of, well, the global flood and accelerated decay, Dr. Snelling, would have released far too much heat. It would have cooked the planet. It would have killed Noah and the ark animals and so on and so forth. But the presence of radiohalos, which is powerful evidence for accelerated processes like accelerated decay, the best the critics have had to offer don't work. The argument from radiohalos and fission tracks and everything in combination, obviously the helium and zircon crystals, powerfully suggest accelerated decay. But at the same time, with what you're saying now and then in your presentation, at pretty lower temperatures, those radiohalos are obliterated, which means, okay, the heat that was released must have been dealt with. There wasn't a heat problem, or else those radiohalos wouldn't be there in the first place.
Correct.